Hello, welcome to the second video in this Calculus 1 playlist. In this video, we'll be covering some of the essential prerequisite knowledge required before we begin calculus. So I'm going to be talking about the real number system, set notation, and interval notation, and discussing kind of their importance and some general things to understand before we begin. So calculus itself depends on properties of the real number system. Real numbers are just numbers that can be expressed as decimals. Let's write that down. So we can write 5 as 5.000 repeated, negative 1/2 as negative 0.5550 repeated, or 500 repeated, sorry. Root 2 is 1.4142, and so on. And pi is 3.1459. So these are numbers that can be geometrically represented on a number line, which we'll touch on shortly. To denote real numbers, something mathematicians and engineers use is this symbol. All this means is that the number or the variable you're referring to is an element of this real number system. But how do we break up the real numbers? Like, what is a real number? What are the different components of the real numbers? So I'm sure you're all aware of integers, whole numbers, rational numbers, but let's define them properly. So an integer is all the whole numbers, 0, and negative numbers. So we can write those down as, let's go, -5, -4, 0, 1, 2, and so on and so forth. Note that these numbers are not fractions or decimals. So an integer value is not a fraction or is not a decimal. It's represented as a whole number. Whole numbers are all the positive integers and 0. So let's write that down. So some examples would be 0, 1, 2, 3, and so on and so forth. So we just exclude all the negative integers from our set for whole numbers. Natural numbers are just all the positive integers excluding 0. So we can go ahead and say that the positive numbers 1, 2, 3, 4, 5, so on, so forth. A rational number is any number that can be expressed as a ratio of integers. So let's say that R is equal to A over B, where A and B are integers. Some examples would be 3 over 2, 5 over 3, -6 over 1. These are examples of rational numbers. And intuitively, an irrational number is any number that can't be expressed as a rational number, such that R cannot equal to A over B. A and B are integers. Some examples would be root 3, -√6, root 2, so on and so forth. And I'd like to point out here, I mentioned pi. It's actually a transcendental number. but that's kind of beyond the scope of this course, but just for accuracy's sake. So moving on, let's talk about our discussion of the number line. What is a number line? A number line is just a visual way to represent the number system. So I'll write easy way to represent the number system. Let's put some integers on it. Apologies for not being accurately spaced. So you can see we have these whole integers represented on a line. We can plot rational numbers. Let's put an irrational first, root 2, irrational. Rational numbers, 1/2 would be here. Decimal numbers, real numbers, 1.2. And so on and so forth. We are able to represent all the numbers in the real number system on a number line, which is very useful. Recall in our previous discussion, we said that calculus depends on the properties of real numbers. But what are these properties? You've probably already seen algebraic properties before. When learning your basic arithmetic or algebra, you learned that if you had an equation such that 3x is equal to 2, that we could divide real numbers to find our solution, such as x is equal to 2/3. The algebraic properties roughly state that we're able to add, subtract, multiply, and divide real numbers and preserve arithmetic sequence. One property you've probably never heard of, the completeness property. Roughly speaking, this says that there can be no holes or gaps on the real number line, and that every point corresponds to a real number. We're not going to deal with this much in our study of calculus, but know that exists. The property I want to focus on the most is the order properties. Order properties. What do these mean? So the order properties depend on inequalities. Inequalities are statements using Boolean operators that state the condition or state of numbers. So what are these Boolean operators? You've probably seen them before. Less than equal to, greater than equal to. Using these, we can kind of state conditions between real numbers. We can use the real number line to look at something called intervals. Let's talk about some rules for inequalities. Using that set notation of the real numbers, we have A, B, and C are all in a set of real numbers. So let's say we have A less than B. If we add C to both sides, A plus C, and we have B plus C, we see that the sign is preserved, that A plus C is still less than B plus C. If we subtract C, so A minus C, B minus C, we see that the sign is preserved. In this case, we have A is less than B and C is greater than 0. This shows that AC is less than BC. In the case that A is less than B and C is less than 0, we see that AC, is now greater than BC. Make these symbols look better. And just thinking this conversely, let's look at this. Let's say we have 1 and 2. Then if we do C is equal to -1, then 1 times -1 should be less than, or should be greater than, -1 and 2. And we know that -1 is greater than -2. So that's kind of what we're referring to. Another rule that we should look at is when a is greater than 0, we know that 1 over a is bigger than 0. So for example, let's get a is equal to 2. Then we know 1 over 2 is greater than 0, for example. And last but not least, for for a is bigger than 0 and less than b, then we know that 1 over b is less than 1 over a. So we could go a being 1 again, b being 2. We know that 1 over 1 is bigger than 1 over 2. So moving on, let's talk about set notation. Set notation is just a way of writing down a set of elements, objects, inequalities of anything. So we write them with curly brackets. And it's a way of writing a set of objects. Note, I didn't say just numbers. They can be anything. So for example, let's call the set of A. That could be, this is what I mean by a curly bracket, 1, 2, 3, 4. That could be the set of A. Let's say the set of B is the set of best soccer teams in the world. For instance, say Arsenal, Man City, Real Madrid, for example. So they don't have to be numbers. It can be anything. The next type of notation I like to write is interval notation. Interval notation is the way to describe continuous sets of numbers. So let's write that down. The way to describe continuous sets of numbers. So how do we do this? We introduce something called intervals. Intervals are bounded sets of numbers that lie between two fixed endpoints with no gaps. So let's write that down. Let's go to the number line. Let's write down some integers. Let's say we want to represent the numbers in this interval. This would be all the real numbers between -1 and 1. We would write this is known as an open interval, as -1 to 1 with open brackets. This is because this little open circle means we're not including the endpoints, so we use round brackets. No endpoints. So if we wanted to include the endpoints, we'd use square brackets. So let's try that. This would be -2, 1. We don't necessarily have to use one or the other. Sometimes we use one side open, one side closed. That would be represented like this. This is known as a half open interval. But what about cases when our numbers go forever? So let's say we have this inequality. I'll write it down in yellow. How do we represent that? It's not bounded. We can use the construct of infinity to our advantage. So we would start at 0 with an open bracket, and we would go all the way. So we would represent yellow as 0 to infinity. We could do the same with a closed bracket. To start, we go 2 to infinity. No, we don't include a closed bracket on the infinity. We never reach infinity. Infinity is more of a construct rather than a mathematical number. So it's always an open bracket. You can always go, if you're adding, so let's say you want 1 billion, you can always add 1 to 1 billion. So it's not the end that we're reaching. So we always use a round bracket when we're talking about infinity. Let's look at an example. Solve the following inequalities and express the solution sets as intervals and graph them on a number line. So let's look at A. So we have 2x minus 1 is greater than x plus 3. Feel free to pause at any time. For today's ones, they're going to be relatively easy. We're just starting off, so let's go ahead and try it. So 2x minus 1 is greater than x plus 3. So from algebra, we know we need to isolate for x. So let's do this. So adding 1 to both sides, and then subtracting x from both sides, we got our solution right away. Pretty straightforward. But let's draw this on a number line. Let's see if we can represent this properly on a number line. Let's start 3, 4, 5, 6, and this one goes back way. So since ours is x is greater than 4, our solution looks like this. Open circle, extending all the way to infinity. In interval notation, we write this as open bracket, since we got an open circle, no equal sign under, and then we go 4 to infinity, open bracket. And that's our solution. So this is the interval form, this is the graph, and we have our solution, our inequality. So for B, relatively more involved, but still very simple. We have 3x minus 1 is less than 5x plus 3, which is less than or equal to 2x plus 15. So what I like to do in these types of problems is break it down into 2 halves. 3x minus 1 less than 5x plus 3. On this side, 5x plus 3 less than or equal to 2x plus 15. So starting on the left-hand side, we have 3x minus 1 is less than 5x plus 3. Let's put all the x's on one side and all the numbers by themselves, the constants by themselves on one side. So we would subtract 3 onto this side, and we would subtract 3x to go onto the other side. So let's do that right here. Minus 1, minus 3, and then we've got 5x minus 3x. This becomes negative 4. This becomes 2x. So solving, we get x is greater than negative 2. On the other side, follow the same thing. We'll get 5x and 2x on the same side and 3 and 15 on the same side. So we'll get 5x minus 2x less than or equal to 15 minus 3. This leaves us with 3x, 12. We get x is less than or equal to 4. So now we have these two inequalities. How do we represent these on a number line? Write these a bit more compact. 2, 4. Good. So here we have negative 2 is, x is greater than negative 2. So we go to negative 2, and we have an open symbol, since it's just greater than, not greater than or equal to. Then we go all the way till 4, where we have it x being less than or equal to 4. So we close our circle. We call this a half open interval because one side is open, one side is closed. And to represent this in interval notation, fairly simply, negative 2, open bracket, since it is an open interval, we don't have any sign under here. And on the other side, we go till 4 with the closed bracket, since we have the greater than or equal to, or sorry, the less than or equal to symbol. And this is our solution. So overall, we touched on real numbers, what they are, some classifications of subsets within the real number system, so integers, whole numbers, natural numbers, rational numbers, and irrational numbers. We talked about representing the numbers in the number system on a number line. Then talked about the order properties of inequalities, which we'll touch on in a bit more detail in further videos. Talked about set notation, the way to write down a set of objects, which can be elements, it could be numbers, it could be anything, it could be football teams. And then interval notations, how to represent sets of numbers with inequalities using the order notation. So yeah, if you enjoyed, feel free to hit the like button, and I'll see you in our next video.